Stoichiometry is the process by which the amount of one substance in a chemical reaction is related to the amount of another substance in a chemical reaction. And remember, the coefficients that we see written before the compounds in a chemical reaction relate the moles of those compounds to the rest of the moles of the other compounds in the chemical reaction. And mole is simply a measurement of molecules, right? 1 mole equals 6.02 times 10 to the 23 molecules of that compound. And so how can we use stoichiometry to determine the either the molecular formula or the empirical formula for a compound in a chemical reaction? Remember, the definition of a molecular formula is a chemical formula that provides the exact number of each type of atom in a molecule. In contrast, the empirical formula is a chemical formula that provides a simple whole number ratio for the atoms in a molecule. All right, so a little bit less detail there. So what we're going to do is kind of work through example 8.12. And while I know that it's written in your textbook, sometimes it's just easier to kind of walk through and see visually what's happening. So you can kind of look at things in your book, or what I recommend is writing things as you go, right? And thinking in your mind, what exactly are we looking for? So in the textbook, I've written down here is the information that is given in the word problem, and then what are we looking for. So a compound, an unknown compound that you're working with in the lab, is decomposed, meaning broken down into its constituent elements. And what they found is that there are 2.34 grams of nitrogen and 5.34 grams of oxygen when they do this decomposition reaction. And the question then asks, what is the empirical formula? So what do we know from this information? We know that there is some compound that is formed by the bonding of nitrogen with oxygen, some unknown compound. And the reason we put the subscript X and the subscript Y is because we don't know how many atoms there are of nitrogen per number of oxygen in this relationship. So that's what we're looking for, is what is this relationship between nitrogen and oxygen in the original compound. However, what we do know, because it is a decomposition reaction, on the right side of the arrow, what is going to be produced is nitrogen and oxygen. And the other thing to keep in mind, right, we build on all of the material and information that we learn throughout the each module, that nitrogen and oxygen are both homonuclear diatomic elements. So when they're written in an equation like this, we have 2 atoms of nitrogen linked together to form nitrogen, and we have 2 atoms of oxygen bonded together to form oxygen. So this is then the chemical reaction that was run in this experiment. And we know that the mass of nitrogen, when we ran the experiment, that there is 2.34 grams of nitrogen and 5.34 grams of oxygen. Well, that's great that we know the mass, but this relationship doesn't relate the mass of these substances, it relates moles. So the very first question you must ask yourself is, right, well, there's 2, right? For nitrogen, how many moles of nitrogen, or molecules, are there in a 2.34 gram sample of nitrogen? And secondly, how many moles of oxygen are in a 5.34 gram sample? So we will begin with nitrogen. If I have 2 atoms of nitrogen and I look at my periodic chart, one nitrogen atom has a mass of 14.0 AMU. Since I know how I have 2, I'm going to add those or multiply by 2, and I know that the mass of 2 nitrogen atoms is 28.0 AMU. This number tells me that if I weigh out 28 grams of nitrogen in the lab, in that 28.0 gram nitrogen sample, I have 1 mole of nitrogen molecules. this becomes my conversion factor. So I can take my 2.34 gram sample and I can divide by 28.0 grams of nitrogen, and that will tell me I have 0.0836 moles of nitrogen. And the reason I have 0.0836 moles of nitrogen, and I didn't round this at all, is that this number, there are three significant figures. These first two zeros are non-significant, 836 are significant here. So then I will do the same thing for oxygen. One oxygen atom has a mass of 16.0 AMU. Since I have two, I will multiply that number by 2, and so the mass of O2 is 32.0 AMU. So in a 13.0 gram mass of oxygen, I have 1 mole of oxygen molecules. So I take my original amount up here. We're given that we have 5.34 grams of oxygen in our problem, and I will multiply it by this conversion factor, because I know I want the 32.0 grams of oxygen in the denominator, because I want the grams per oxygen to cancel, and I'm left with moles of oxygen. So again, I have three significant figures. I have 0.167 moles of oxygen. So in my original, instead of just in the way this chemical reaction is written here, this implies that I have 1 mole of nitrogen for every 1 mole of oxygen. And that's just kind of, usually we like to write in whole number integers for those moles. In this case, that's not really what we have, right? So what we've discovered is that we have 0.0836 moles of nitrogen for every 0.167 moles of oxygen. So how can we convert this to whole number integers? Is we simply divide by the smallest number, and that would be our 0.0836. And with this, if you do that division, of course, that means this becomes a 1. We have 1 mole of nitrogen for every 2 moles of oxygen in this decomposition reaction. And so then, of course, this tells us that we must balance the equation, right? So in order for this to be balanced, that means I have to have N2O4 as my starting substance. However, this just tells us a little bit about the ratio, right? This could also be, if I multiply both of those by 2, right, this could be N4O8, and then we would need to adjust these coefficients on this side. So what we really want is the empirical formula. If we go back up and look at the original problem, empirical, it means there cannot be any common factors in the original problem. So 2 and 4 are related to each other in the fact that they have a common factor of 2, and if we divide both by 2, we come up with the empirical formula, which is NO2. And that becomes our empirical formula. And we'll do another one here in a little bit, but hopefully this will help.